So yeah, in some sense, the goal, at least, so the goal is again the categorical conjecture, but yeah, we'll be much less explicit about this. So, like Cindy's talk was very explicit, and we saw very beautiful geometry of the set of L parameters. This one we have here. The goal of this talk is to see that most of the things will be quite categorical and can be solved using a check constants. So maybe let's state what the conjecture even is. So let me state it with all generalities, but in the talk we will talk about the restricted subset of the conjecture where a lot of notation will simplify. So if you have questions regarding the notation, I implore you to wait until I get to the simplified version and then ask the questions about the notation. So I suppose the full conjecture with like all declarations, as you choose a quasi split group, or some Archimedean local field E. We have lambda with this algebra, and we choose a square root of Q inside there for technical reasons. And we fix the Whittaker datum. Okay, so then the full conjecture can be stated as follows. There's an equivalence of categories. Oh yeah, also I will choose like slightly different notation from Cindy's talk, because this is how I wrote down it on my notes. So when I write, so this guy here is the same thing as what Cindy wrote as this. Yeah, I've been reading too many geometric Langlands papers, so this is my notation. And this is equivalent to E's, B's, and coefficients in lambda. Such that the structure sheaf goes to the Whittaker sheaf, which is the Schrieg extension of the compact induction. Yeah, I will usually just call this W. Okay. And also, okay, so I mean, it's not just as plain categories, but actually these categories have additional structure. Namely, they are acted upon by perfect complexes on a stack of L parameters. So this is supposed to be S. And yeah, categories.
You told us not to ask about notation, but I have a problem that I can't even read some of the notes.
That's fine. Just ask me what is like.
So the compact induction is from where to where?
Oh yeah, so this is from U to G. So UE to G.
And E?
E is the field over which the quasi-split lives.
Thanks. And the ban
G
is G, and for the LS, it's also a G?
No, this is supposed to be the Langlands dual group of G.
Not a G and not a C.
You can try to write a little bigger.
Yeah, okay. Well, yeah, so E, I guess E, but we don't need most of this notation, but I mean, I guess has residue field in practice with E, and P is not equal to L. So that answers the question. Very important. And also it should send compact objects to compact objects. Yeah, so in particular, with this statement here, this is actually the same conjecture as forming Fargues-Scholze, where and there's no in category here until they take compact objects. Okay, and just to ease the notation, I mean, this has a lot of stuff. I wrote this right, D of 1D as DB's 1D. That's my idea. Okay, this is quite messy, and there is a lot of symbols. So let us single out a certain open substack in there, in which case the conjecture becomes easier. This is the irreducible part that was in the title of the talk. Because, okay, the title of the talk was about the irreducible case. So let me say that the conjugacy class of L parameters is irreducible if it does not factor to a parabolic. Okay, so for GLN, for example, this is, okay, example, if P is equal to GLN, then irreducible means irreducible. So classical notion of irreducibility. Okay, and so then there's also, using this, one can define an open substack of irreducible parameters. Yeah.
Split, what does it mean?
It's the dual group then.
Yeah, we're living on the dual group. So the dual group is
Dual group is a complex group.
okay, but in this business usually one considers a dual group as well something living on the inside as well. Maybe once the
Yeah, that doesn't answer my question.
Maybe this is the easiest fix.
You probably mean the cosine, like the cosine that doesn't factor through.
Yeah, I mean, I will write down the more precise definition here, and maybe this will answer the question, and if not, I'll just but I mean, in the end, I'll assume
The
that
question, there is a notion of parabolic subgroups of L groups. Those are the
Right.
ones that are somehow
Okay.
centralizers of co-characters. I mean, that I'm effectively a standard definition of these, but I
Okay.
agree that it
Okay.
requires some explanation.
Yes.
and this is the complement. You can also describe this as the complement of like the image of the net from. Okay, and I guess now there is a question like, what it is for this guy to be a parabolic. Well, yes, I guess Pierre's comment about the dynamic perspective probably the best version to choose for this, but maybe that's just assume it's a good test. Okay, this is running over proper parabolics. So in particular, we see that it is actually an open substack because this map is proper, and we take a union of finitely many such closed substacks, and then It is in fact open.
Well, this is the reason that I did not adapt to notation local systems G-check, because G-check seems to only know about the group and not how the Galois group acts. This is why I always was writing this stupid stuff with the one co-cycles. Because I couldn't think of a notation that remembers that we're looking at co-cycles that didn't exclude the data.
Yeah. Yeah, that's fair. But it's also very clunky, so.
It is very clunky. I would like a better notation. Well, but even in the geometric case, I mean, you're also considering only split groups in geometric Langlands. But if you consider non-splits, then you should also. There should be a good notation, but I don't know what it is.
Well, David writes parameters like PAR, but I mean, I guess that's not
But even the subscript, yeah.
Well,
You can't just write G-check.
We'll figure out some notation at some point. Okay, and then the conjecture that we're actually proving is for G equals GLN. So this conjecture is the case. Quite low. So I mean, probably a lot of notation there, but we just tensor over this curve. Oh God, it's not enough space.
Go vertical.
Yeah. Okay, so I mean, basically, it's everything that I've written down here, but we just tensor over the curve on the same operators, curve on the same operators, but they reduce the operators. And again, I mean, there is the structure sheet here, and I'll explain soon how to make this more explicit. I mean, goes to this one J already. Well, okay, so this is an open substack, so it has an inclusion, which I call J, to the entire thing. Okay, so basically one again has to match a certain object on the left-hand side to an object on the right-hand side. And it's the one that you're basically forced to when you tensor these categories with each other. Okay, so this is somehow not really explicit. I just wrote you some tensor pair of categories. In fact, so in fact, both sides can be made very explicit. So remark. Okay, so left-hand side can be made explicit in the following sense. It is the same thing as, well, so this is just in colloq on the irreducible guys. And okay, in fact, this is equal because we're working with irreducible guys with int per the quasi-compact support. So this is what the QC means in quasi-compact support of these guys. And the nil condition becomes 0 for irreducible parameters. So yeah, this becomes inferred. So yeah, so that means I do not have to explain what the nil condition means because in this case it just disappears. On the other side, well, at least one can say that the right-hand side is a full subcategory of phi of bun G. One can be even say that it's a full subgroup phi of bun G semi-stable, and this is just the same thing as the product of B and BG basic of the derived category of representations of GP over B. And one can also describe the essential image of this fully faithful embedding. It's those representations here with whose subquotients have Fargues-Scholze parameter being irreducible. So one can be very explicit what this means. But okay, for the intuition, you can ignore the fact that bun G exists somehow and just pretend that it's a full subcategory here, and you don't have to worry about the nil. Yeah, so that's why I said to wait until the notation simplifies.
But what do you need to do?
Where?
Yeah, even in your remark, you still need to gain. What do you need to see?
Well, I mean, it's only the in category is you basically add all filtered colimits. Or do you mean why I write it here?
Why don't you just consider the completion of the category? But the in category.
There are certain advantages of work. So the point is that you don't add int, these categories are idempotent complete and they have all small colimits, not all. They have finite colimits. If I add in, they are presentable and they have all colimits. There's a slightly more flexibility allowed if I work with presentable categories instead of just compactly generating ones. I mean, okay, so like the main point here is that there's a small difference between working with PRL and PR compactly generated. And there's like a little bit more flexibility here, but this is a more subtle question of homotopy, which is like maybe not so important for the talk. But for this reason, I chose to write int everywhere, even though there's no int somehow in Fargues-Scholze. Okay. Okay, so first observation is both sides become quite simple. This and this. The second observation is now that I simplified both sides, like the action, I should say, in the conjecture, this should be, now since we tensored over the inferred action to an inferred, like irreducible parameters action, you can only now say that this is as inferred linear categories. And you should really think of this as like base changing a module from one ring to another ring. So the second observation is that this condition that this is supposed to be linear, this sequence must be linear, the inferred of irreducible parameters determines the functor. So the second remark is that the functor, which is just given by you see through what we call the C, the right-hand side. You see, I mean, which is given by taking an object and letting it act on the vertical guy. And this is the unique functor that could make the conjecture true. Okay, so there's an easy description of our candidate functor, and it's just, giving acting on this one object. And so we only have to check that this functor is an equivalence. Well, we don't have to put in work to produce such a functor, it's already there.
And the sticky question, so what do you mean the stuff or stuff?
Yeah, so this is, what does it mean for a category to act on another category?
So it's mean by the action.
Yes. So this is what I mean when I write star. I mean like A X on W.
Okay.
No. There. Well, no. Yeah. Yeah. Okay, let's see. Okay, there's a big part of homotopy theory that I have here, but maybe I'll. Okay, there are some parts of homotopy theory, but maybe I just skip to the part where, like the main result of the homotopical considerations, and we see in the end if you have time for this. So this is the part where it comes to like categories, schemes. Oh, and this is okay. Okay, so we want to prove that this is an equivalence, and we sort of want to check this in the end, sort of when we localize that individual L parameters, and like sort of a good framework to do this is like by considering like theory of categories or schemes. I know this is maybe not a case theory, but it's probably more classical. And in fact, I will use a more simplified version of this.
Sorry, what does the courtesy stand for?
Courtesy is defined to be the right-hand side here. So I don't want to write this thing all the time. So I'll just call it courtesy. Like, I mean, for example, if you take this, if you take lambda to be the rationals, then this would here cut off sort of the superclassical Lagrangian components and each of these guys here. So, yeah. So for this, we fix y in the Hecke scheme. And the point here is still a category over y. At least for this talk. Is a module over one different piece on y. So maybe for those who know the language, it would be like something like modular objects in okay, and here, so the main observation for this type of settings is first of all, in the memo is that you call y. Also, I could stress that I mean, whenever I Q-code, I really mean like the right category, just to make it clear. So Q-code is generated.
What is the definition?
So when I write Q-code, I mean like.
I mean, it says definition and then.
The category of y is a module over quasi-coherent sheaves on y in.
I don't know what that means.
Yeah, basically means that Q-code of y should act on.
I mean,
On the category. I mean, it's precisely the type of setup that we have in the factual action with a category and
I don't know what that means.
What's PR?
presentable infinity categories with left adjoint functors as arrows. I mean, so intuitively it would be there is a map Q called y, which sort of is the action map. Plus higher coherences that I don't want to explain.
And by QCO, you just mean input, right?
Yeah, so since we are working with the Noetherian scheme, it's the same. In general, yeah, I should work with input. That's good. Yeah. So that's the definition of roughly the idea of what it means for category to be acted upon by different sheaves. Okay, so this guy is generated. By the push forward of individual points inside line. This is like classical, so I leave this as an exercise. And one consequence of this is the following. So if we define, so we have a category with scheme, so maybe it would also make sense to talk about individual fibers over individual points of the scheme. So we write Py to be we basically base change from Y to the individual point. And the observation we want to make here is that so maybe similar to the classical situation that this functor here is conservative. Okay. And just so we don't lose track of what we want to do, we still want to prove this conjecture. And why is this useful? Well, how do I prove that a certain functor is an equivalence? Well, in case that we have an adjoint, it's about checking whether the unit and the co-unit is an isomorphism. And so in this case, if we know such a statement, well, checking that things are isomorphisms can be all done in these categories, and maybe these categories are more simple. So that's why we're doing this notation here. The problem is, however, that well, this definition is still like sort of too abstract to be helpful for us. In particular, the categories that come up here don't admit a nice, simple description. But we can fix this.
I ask, do you need all points in the space of Y, or is it enough to choose close points?
Since we're working with Q code, close points are not enough. So and I thought about this question a bit, and in a sense, if you can say that the category Y should be in a suitable sense a finitely generated, then it should be enough to only consider closed points. But I couldn't make sense of this notion, so I didn't try to do so. There should be a statement like this, though.
You just took the push forward from the generic point. What do you know? Generic points.
Yeah, but the point is that push off the generic point is not finitely generated. So that's why I'm saying that sort of if we are finite in a finitely generated situation.
Okay. Well, basically never for these kinds of.
Yeah, so in the formulation right now, probably not. And sort of what goes on here, I think, is like this famous computation of the like Baumol spectrum of Q co of Y, and then you see that it covers the points of Y, and so it's like something like this. Okay, so we want some version of this lemma where the categories are more easy to understand. And for this one can instead consider following thing. I think of this as really some type of formal completion where this one we define to be Q over the formal completion. Okay, and so here one should probably be careful. So here I probably mean like the closure of the modulus thing. Like I mean, if y is not a closed point, I should take really its closure and then write it like this.
If y is a generic point, what does it mean?
Well, if y is a generic point, then so I mean this. So this is like the shorthand notation or particle sheaves that are supported set theoretically on the closure of y. So if y is the generic point, I mean this is Q of y, this is Q of y, and then
It's about trying to reduce complexity.
We'll get to that. But there will be another trick involved where one reduces this problem to closed points, and then you go to closed points, but instead you have to allow for all different coefficient fields. So yeah, okay, do admit if y is not a closed point, these categories are not necessarily that much simpler. The point is that these categories are at least not harder than C. So I mean, the problem with Cy, I mean, this could be like more complicated than C in some intuitive sense. These guys are at least.
You use in the example you care about, is it really problematic to pass through fibers? The stack is smooth or something.
Well, the stack isn't smooth, right?
So in positive characteristic you get.
Yes. I mean, where the goal is to do this integrally. In Perfect Zero, I mean, Senji's strategy he sketched in the last talk is certainly sufficient. Positive characteristics, since the stack is not smooth, one needs to put a little bit more work in the categorical department.
Can you give an example of like what you're doing with this? Like, let's say X maps to Y, where there's
Yeah, I'll look at the content of the next remark, I think.
Okay.
The point is, so this guy here will be a full subcategory of C. And, well, okay, maybe we do like the example that's relevant for our talk. So we take C to be, well, this guy up there. But we'll see, what's it like C equals C? That was a very bad notation, so I guess I just write C equals Q upon D. And Y is something like the cross moduli space of P hat. I guess I don't have a better name for this than just writing like this, but whatever. Okay, I mean, there's a small thing that Y in this case is not really an Noetherian scheme, but it's an infinite disjoint union of Noetherian schemes. But I mean, this is a minute difference. We take maybe Y a closed point in there. Okay, in this case, C, this is the full subpair of P of E. Here we assume that this is like irreducible. So we can here take semi-simple, so look like it's the same thing as to make it even simpler our lives. And this the full subcategory is such that generated by those F inside there is such that subquotients, like irreducible subquotients of F and L parameter Y. Yeah, so this is, I mean, there's also an appendix of Linus' thesis. There's a localized category introduced, and it's the same category. Up to, I think in Linus' thesis, like in this appendix, I think they only consider ULA sheaves, but sort of it's the same idea. It's just a more categorical way of writing this. But yeah, okay, so this I think.
But what we are studying is that they are
Well, I mean, the description doesn't become much simpler. I guess here it's like either GL2 or the division algebra, but still, I mean, this one still localizes the category at a certain L parameter, meaning it contains like only those representations whose subquotients only see that L parameter. I mean, I don't think for GL2 the description becomes much simpler. I think this is already pretty.
Firstly, you assume the parameter to be irreducible. What if you drop the condition of irreducibility?
Well, it's basically it's the same thing basically. It's just that.
Yeah, this side is what explicit, but giving the description of the object is still the same.
Yes. In some sense, for any category C, this thing here is given by those objects where the action sort of factors through Y. So if Y is an affine scheme, you can sort of literally make sense of this as like factoring through the residue field. And in general, I don't think you can make sense of this literally, but maybe intuitively, you could think of this as the action factors through like point given by Y. So in particular, one sees that if Y is a closed point, really, I mean, your life becomes a bit simpler here. Because you will really only focus on a single parameter. And if you know compatibility, which for GLM we do know, you can like really say, I mean, this will be the representation that is in that L packet, and then it becomes really explicit.
Actually, in this example, can I also say what the fiber is instead of the local?
The fiber is okay. So this is, I mean, actually, this is part of some paper I think of Johansson and Christian Johansson and Hans. Yeah, where the point is this like modules over you push forward the structure sheaf in. Well, I mean, this is abstractly true always. And when I say that your life becomes a bit harder, the problem is that, I mean, what's this? And, you know, that becomes like a bit harder because there it's like, you have an object in there, but additionally it has an action of like this ring. And okay, and if you're in characteristic 0, you can make this ring probably very explicit. But in general, I don't know if one can make it so explicit. But people do think about this situation too, so don't get me wrong. Like these fibers, they are also like some people think about that. It's just not for my Okay, since Pierre already made the remark that that these guys here might not be that much simpler than the original guy. So I didn't, well, it's like not part of my notes of the point, so. How to reduce to closed Y. Well, basically, it's like a pretty basic observation. The point is if at Y, this is the point inside Y, then if you take a final product, like, okay, maybe we say both of this over some base spec of K, then the final product, let me hope that language is correct. Well, okay, so this fiber product sort of has canonically a closed point. So this Y prime, which is like sort of this point Y. So basically the idea is, well, here we need to consider all the points, but if we allow enlargement of the base field, then if we base change along the inclusion, like if we base change take y along like this non-closed point, it becomes a closed point. And this is how you reduce the closed points. However, you will need to allow enlargement of the coefficient rings. So this is the type of trick. Actually, this is also seen in one of the geometric Langlands 6 author papers. But I think it's in the second one, the first one maybe, where the trick is really just, the base change the point. So maybe this is a bit confusing, but maybe let me just say what's the point of this discussion. So we return to the setting of this conjecture there. And the corollary is pointer which is linear of the Fargues-Scholze center. And note if you are linear with respect to like this entire category of imperfect complexes on the set of locuses, then you also automatically have this weaker condition of being linear with Fargues-Scholze center. This one is before the break. Then we write the coefficient here for now. If for all semi-simple parameters valued in all, it's important that we take all fields, but here we can assume algebraically closed that we have. So all algebraically closed fields K over lambda, so we call it phi, from our parameter from E to K, like this localized functor is an equivalence. And there is a certain computation involved that on the right-hand side, the localized category is, in fact, sort of those incoherent sheaves that are set theoretically supported on this parameter y. But once you have to base change this to like k. And this is equivalent to also this localized at phi on E and the coefficients are k. So yeah, the trick is somehow since I didn't really say what the ring is, I give myself the freedom to not only prove for a specific ring lambda, but like really all rings lambda at the same time. And this sort of makes the proof a bit easier. This should be outcomes giving rise to closed points. Yeah.
So do you mean to say that the lemma of being is conservative also holds for the localization?
Oh yes, yeah, that's also true. The point is that taking the fiber from the formal completion to the fiber is conservative, and this is some sort of derived Nakayama lemma. Yeah. I should have mentioned that.
If you take all points, then you have all the generic points.
Yeah, of course. So in some sense, it's like boring. I here already made the observation that if you take y to be the generic point, I mean, I'm not saying anything really. I mean, the trick is really that if you allow yourself to vary the coefficients,
the conservativity is much easier than that.
Yeah.
It's corollary, don't you need that the right adjoint functor is still only removing?
What does the corollary say? I don't see a sentence here.
Well, I'll say here preserving compact objects. But yeah, I need that the actual is equivalent preserving. That's true. Thanks for that comment. Oh, sorry. Okay. Is equivalence if this line, the local that is an equivalence. So really we have simplified the problem from, and also this holds if we restrict to open subsets in the same way we do it in the conjecture. In the irreducible case of conjecture. So yeah, the point of this is that now you only need to consider like the formal neighborhood around an individual L parameter in the stack of parameters. And the point is that this will be easier to do than, well, this is the part where you are able to circumvent Sinji's result, because so what Sinji does is like, well, he really precisely analyzes how the stack looks like, how these connected components look like. And then using this, one can deduce the categorical conjecture. Whereas here, once you have this corollary, you only need to look at formal conditions around like such an L parameter. And there are strong theorems which tell you how these look like. So there's this paper called lisse-etale theorem for algebraic stacks. And this like really tells you a lot about how these formal neighborhoods look like, which will be in fact the content of the next.
Yeah, but so here you're writing the fibers or completions.
This would be completion. Yeah, I don't have a good notation for completion, but
how about the right side? The right side, it seems that you
also, yeah, this is also like this will be this in the notation there. Yeah, I apologize that notation is a bit off here, but it's like this is both about formal completions.
So before in the categorical scheme, you write the y, but what's the y in this corollary?
Y is it's this situation. Or maybe one takes here C, well, technically one should take here C to be the C up there, and for here Y to be the components correspond to the irreducible parameters. But yeah.
And is it a scheme? So is the local system a scheme?
Yeah, this is the coarse moduli space, so it's a scheme. And this is in fact an infinite disjoint union of affine schemes. So this has a really simple structure. Oh, okay, I mean, some parts of this are hard, but like it's an infinite disjoint union of affine schemes.
You change the assumption from the full transaction to just this thing. Say the first thing.
Well, because I said Y is in the theorem scheme and the stack of stack of L parameters is not in the theorem scheme. I mean, there's also some version where you can replace this with the stack, but I was too lazy to think about how to make this all work out. And you also don't need the full strength. So, I mean, everything also lives over the coarse moduli space, of course. And so it was like easier to write it in this way. And it's really, yeah, one could have done it with the full stack. It was just easier mathematically to write it down like this. Maybe I'll keep the part where we write, where it's written down what we actually have to prove, so we don't lose track of that. Okay. So let me explain some claims of the local structure of the stack.
But yeah, so because it's for y, the local system is the infinite disjoint of the band scheme, so it's not serial.
Yeah, but like each connected component is a theorem, and the difference between like going to like an infinite disjoint union versus a single compound is not that big. So I do agree there's something to be done. Yeah. I mean, yeah, all as it's like written in Fargues-Scholze, I think it's like the difference doesn't matter. Well, there's some trouble. So the next part is about the structure. And here we assume G equals GLN and phi is irreducible. So in particular, this implies, which is actually the main point, that the centralizer of phi is the center of GLN, and that's the main point. And in the interest of time, let me just cite the conclusion that comes out of the, let's say here, which is the perfect complexes on this guy here. Okay. Maybe I should say the observation first, and the observation. So the general setup is like roughly seen with X, which is the quasi-separated algebraic stack over an algebraic equals field K. And we have some X inside here, and so of course there's a dx, which is the stabilizer of X. And there's also a normal space 2x on which field x, and in the interest of time I will not explain precisely what that means. And in the situation here, so for if x is this guy here and phi is of course irreducible, then the point is that of course p of x is like this is something like the center of GLN, and the action, I mean, since this is the center, is trivial. And once you make this observation, it sort of follows from that it didn't write down, but this is red, this is alpha, what's H? Okay, I forgot what H was. Like, this is the lunar half, I assume. Implies that the structure of perfect complexes is the following.
Sorry, what was NX here?
Wait, can you repeat the question?
NX.
So that's a normal space, 2x. So this is the x is given by some ideal sheaf ix, and this one would be like I, and it's not ix squared. Maybe I have to take duals. Up to duals. Maybe I have to take a dual here. But probably that's the idea of the normal space.
So what is the observation?
The observation would be then that like this is then isomorphic to like the formal stack where y is an affine scheme and gx acts on y trivial.
Why does gx act on nx trivially? Is that something specific about the?
Yes, this is specific about the case of GLN and irreducible parameters.
That doesn't know it doesn't.
Yes, exactly. So yeah, the observation is sort of that at the formal completion, it looks like the stack with the trivial action of the centralizer. Of course, if we have Timothy's results, we already know this, but I mean, sort of the point. Well, back when I wrote this thing, these results were not available yet. And also, I mean, the observation works in this type of generality. So, I mean, really, you only need this part of the observation. This works for every phi who centralizes the center. And then one can apply lisse-etale theorem, basically, or one has to look a little bit into the proof, and then one obtains a description of the perfect complexes. And I mean, okay, this decomposes as a direct sum of the characters of the center. Okay, let me write the notation which will make it true for like all the note for GLN, of course, the action of the Gara group is superior. Okay, and so what do these words mean? Well, so this guy here is the full subcategory such that the center acts via chi. In addition, there exists like a line bundle of chi inside perfect complexes here, such that, I mean, this line bundle induces often equivalence between the zero part and this should be localized. And the chi part. And in addition, one can describe the path where the action of the center is trivial. And follow. And yeah, so okay, we call like this to the coarse moduli space that is called this map. Hi. And then there's also addition equivalence by pulling back from perfect complexes of the coarse moduli space where you localize at phi with perfect complexes of this guy here, localized at phi, where you take the puzzle syntax trivially. Okay, so I mean, this is like the observation. This is like basically followed from the lisse-etale theorem. One has to be okay, and maybe some parts that are written like in my master thesis. And so additionally, so once you have this, in particular, once you have these line bundles here, which allow you to change the action of the center, the corollary is in this situation. So D equals GLN and phi irreducible. L phi, which goes from curve localized at phi to this guy here, is equivalent if only if sort of the degree 0 part is 0, and here degree 0 means on D, and the component well, the connected component corresponding to 1, but actually, since we're irreducible, one can also just take a neutral stratum here. Okay, I could remark that this is a subcategory of P of GLN. So we're really explicit. We're really just working with representation of GLN E, and this guy here via this lemma should be also easily understandable. So this one needs a certain compatibility between the grading on the left-hand side coming from the action of the center and the grading of the right-hand side coming from the connected component on E. Yeah, this I verified my master thesis, so it's fine. Okay. And now the goal is to prove this guy here. Observing that this category here is really more a closed, it's like really closely related to like, or it's basically modules of a ring. So we're in the setting, oh yeah, sorry.
What is the statement about pi star? Like, star, but
It's equivalence. Yeah.
So, could you go back to the problem in the beginning? I mean, if you take J is just split, then the gamma action is a trivial. So, how do you make sense for this split group?
What do you mean? Like except of what for quantity?
It makes sense for J is as a split group. Because if you take the J as a split group, then the gamma action of this split group is that trivial action.
Yeah, so I mean, like I wrote it in such a way that would also make sense for quantity groups. Like I mean, the area here would have to take invariance out of the Galois group of the center.
Yeah.
So this statement, so I mean, I only wrote it down for GLN, but like, I mean, as I wrote it, it will also apply to other groups. Under the assumption that the centralizer is the center of the, well, the Galois invariant center of the group. Okay, we're left to prove this, and we're like already out of time, so we give a short sketch of this. Maybe, okay, we need some lemmas about the Whittaker guy, which I will have more time to prove, but this is projected. And also, if you, I don't know how to write this, but this is like the step argument. That is even compact projected. Okay, so we'll just have to believe this. And also another lemma is that the spectral Bernstein center is isomorphic to the endomorphisms of the Whittaker guy. Yeah, we'll also have to take this one on faith, but this is a result of that spread out onto different papers though. It's like, yeah. And then, okay, there's like a small subtlety regarding connected components, which I'll try to ignore. So our situation is something like this. And inside here, there's a compact objects with guys over the endomorphism of the Whittaker guy. And in fact, one can check. So this diagram, like all arrows are linear of the spectral Bernstein center. And one can check that there's a factorization here. Basically because this guy here is generated by the structure sheaf. The structure sheaf maps to the Whittaker representation. And this embedding here is the embedding of the subcategory generated by the Whittaker representation. So there's a factorization down here, making this commute. And then we come to the conclusion on how to show the equivalence. Oh, I mean, actually, I can. I'm looking at the blackboard, so I can add some text. So this is basically our LG functor with the contact objects. Maybe I put here irreducible in this case. Okay, and what can we do now? Well, we have checked that it's enough to localize. Check this after localization. So we localize everything. Okay, so it's sufficient to check that this guy here, this arrow is an equivalence. But using this corollary here, it's even sufficient to go to like the zeroth component. So here we can add one. I should have maybe added colors. Okay. And so it's like nice to add some colors here. So like as a first observation, one can localize to individual parameters phi, and the second observation is one can additionally just go to like the component for 0, and this is the neutral stratum. And so in this case, after we added all these decorations, this one is an equivalence. This guy is an equivalence without all the decorations by this statement. So maybe I give this lemma name, I call this lemma A. Lemma A implies that this is an equivalence. Dash arrow equivalence. So the only thing that, so this, after you localize everything, this is an equivalence, this is an equivalence. So we only have to check that this guy here is an equivalence. So check that perfect, after you localize here, like the embedding into E by bun, at the neutral stratum, is equivalence. In this case, it's enough to check that it's a conservative right adjoint. Conservative right adjoint. Brings the board. And up to here. Well, what's the right adjoint? The right adjoint is given by Foming with the Whittaker representation. And the point is that supercuspal representations are generic. And so this guy is, and also this is projective. So using adding these two together, one can see that this is conservative. So this implies that this inclusion here is an equivalence, which implies that alpha, I should have written it. That this guy here is an equivalence, and after all these reductions, it implies that the entire function was an equivalence. And yeah, that's just the point.
Are there any questions for Konrad?
Yeah. So can you, is it possible to make your talk compatible with the first talk?
Yes. So, okay, you do the first talk up until the end. And then you like sew in my master thesis below that one, and then I think it works. So basically, if you know all of Sindri's results, you do not need to localize. Like you don't have to do all these localization things. Like all these color decorations you can remove. Oh, okay, no. You can localize the orange pies, but you still need like the green 0, like the localization to like connected components of stack of power parameters. So I guess you can skip this entire discussion about like formal completions of categories over schemes. You can remove by inserting Sindri's results in there, and then continue the talk like that. You can fuse them together. So I guess in the YouTube audience, you can like fuse it together in their own head and fuse the thoughts together. I leave that one as an exercise, I suppose.
So you're using the usual localizations.
Yes, so this one here uses so it's here. Yeah, I use the usual localizations. I promised in my abstract that, well, I said it's also enough to show that the Fargues-Scholze L-packets are singletons. The point is, if you know that the Fargues-Scholze packets are singletons, there's a map from here to here, and then its fibers would be singletons, and this sort of then would imply that it's an isomorphism. So really, you don't need compatibility fully. You only need that the L-packets are singletons. You actually only even need that L-packets are a single generic member. I mean, that's like the weakest thing you need to have.
But one thing in the combination of these two talks that I would be interested in is assume you first prove this kind of general categorical thing as here, and then you specialize to depth 0, and then as Genji explained, one can both understand the representation theoretic side very explicitly, and it really comes down to the representation theory of the finite reductive group, but like over ZL, so it's not trivial. And then someone Genji, he's cited the theorem of Fourier that this representation theory is equivalent via the linguistic induction to just representation of the torus.
Yeah.
But could one instead reverse the logic and somehow take this categorical local Langlands correspondence and deduce something about the modular representation theory of finite reductive groups?
Well, I mean, since the categorics are equivalent, one can, well, I guess, since the categorics are equivalent, one only needs to understand this, but I mean, that's sort of a trivial observation. Yeah, I guess.
Like, maybe part of my question is like in the theorem of doesn't tell. Maybe it deserves the status of the theorem. Is there? I mean, what are the ingredients there? Is there some?
Yes, they do. They do. So this has two parts. One is to show that the spectral Bernstein center is the usual Bernstein center, and the other part is that the usual Bernstein center is isomorphic to, and also Whittaker in the theorem case. So for the second one, usual Bernstein center is isomorphic to this. I mean, this is hard, but I mean, it doesn't really use, it's like maybe similar-ish to the character zero case. And in the proof that the spectral Bernstein center is isomorphic to the usual Bernstein center, they do reduce to depth 0 and use a linguistic induction argument. So yes, it's like sort of.
That's too bad. Okay.
Yeah. But I mean, I can say that you can probably. I mean, like I said, if you know that the Fargues-Scholze packets are singletons, you can prove the isomorphism without the linguistic induction. And then, since the isomorphism is unique, you can deduce it's the same thing as the Dartown one. I guess you could wonder if you can then reduce engineer from that to the linguistic that they do. I guess that's interesting. I mean, okay, what I may want to say is, as they prove it, they use the linguistic induction argument. You can circumvent this if you know compatibility. And yeah, but I don't know. So if you can run around in reverse somehow. So yeah, I don't know.
All right, we're a bit over time, so I think we should just finish now and ask questions after. So let's thank Konrad again.